Hi, today we're going to look at section 9.4, which is about models of population growth. This is a common application for differential equations. So let's consider the two population growth models that we talked about previously in section 9.1. So we talked about exponential growth, where that differential equation is the change in population over the change in time, or the rate of population growth is constant factor of the population. If we want to solve that differential equation, we'll notice that that's a separable differential equation. We can divide both sides by p, giving us 1 over p times dp, and then multiply both sides by dt, giving us k dt. So now we've separated our variables, we can integrate both sides. The antiderivative of 1 over p is the logarithm of the absolute value p, which is, and the integral of k with respect to t is just kt, and we have plus our constant. I'm going to cancel out the natural log by doing the exponent base e to both sides. And I remember that addition inside the exponent is multiplication of exponentials with the same base. So e to the kt plus c becomes e to the c times e to the kt. Because we've defined population to always be a positive value, I can just drop my absolute values. And e to the c, we can just call the constant a. Now, let's consider the initial case, so the case or the population at time 0. So the population at time 0, we'd be plugging in 0 for t. When we do that, we have e to the k times 0, which is just e to the 0, which is just 1. So that leaves us with a. So typically, when we write our exponential equation, we say p of t equals p naught e to the kt, where p naught is just the value of p evaluated at time 0. So one special instance of exponential growth, or one modification that we can make to this, is we can account for things like emigration, like people leaving the population, moving to a different country. Or even you could model this as people dying, or, whatever, being drafted into the military or something. So if we have some minus some constant m, our rate of population change could be modeled by this differential equation. And you're actually going to look at this differential equation in a little bit more detail when you work on the homework. I think there's a homework question number 15, I believe, that I assigned, that you're going to be looking at doing something with this differential equation, that problem. The other type of growth that we talked about in 9.1 was logistic growth. So in that situation, for logistic growth, we remember that the population change should be close to exponential when the population is small. But I want that population curve then to level off when we get close to what we call that carrying capacity. And if you recall, back to 9.1, we said that other way we'd model that was dp dt equals pk, I guess it was kp, and we tacked on this 1 minus p over m. So when the population is small, close to 0, p over m is 0, or close to 0, so the derivative of p with respect to t is just kp, which is behaving like an exponential. When p is close to m, then p over m is 1, or about 1, and 1 minus 1 is 0, so the rate of change should be 0. That's an equilibrium, creating an equilibrium point. And if p is greater than m, p over m would be a number bigger than 1. 1 minus something bigger than 1 is a negative value, so our population should be declining back down to the carrying capacity. So let's not worry about this. So this, again, is a separable differential equation. So we can solve this. So to do that, I'm going to divide both sides by p, and then divide both sides by 1 minus p over m. But I'm going to write that as with a common denominator, so 1 is just m over m. So I'll multiply both sides by the reciprocal of that. And then we still have my dp. And that's going to equal k now, and I'll multiply the dt over. So that's what I'm going to be integrating. Now here, what's the best way to do this? So it gives us this. And the best way to handle this, if we're going to integrate both sides, the right side is easy. The left side, that's maybe not too obvious. So what's going to happen if I distribute that 1 over p through? Well, actually, let's write it this way. Let's write it just as, let's not bother distributing it through. And we'll just call that kt plus c over here. This left-hand side looks like a partial fraction decomposition to me. So just doing this on the other side, m over p minus, or m minus p has to equal a over m, or sorry, a over p plus b over m minus p. So I clear my fractions and distribute my a through. So I have the system negative a, because I have the parts that give me a coefficient for p. There's no p on that side. So I just have negative a plus b equals 0. And then I have a plus 0 equals m, because there's no just regular b term. So that tells me immediately that a is m, and b must be negative m. So we're going to integrate m over p plus negative m over m minus p dp. So this is easy to do piecewise. So the m just is going to pull out front, and I have m times the natural log of p plus negative m, and this is again just an easy u sub. So we're going to have negative natural log m minus p so there's that. And I just noticed I did something dumb here, folks. So let's just go back in time for just 1 second. When I set this up, a is the coefficient on m. So a doesn't equal m. A is equal to, or a plus, yeah, that needs to be 1. So this is going to be then -1. So this would be 1, -1. So I have the natural log of p plus the natural log of m minus p equals kt plus c. So I'll combine those together using my rules for logarithm. And oh dear, I did something dumb here. So this b is supposed to be +1 also, because if I plug -1 in for a, b would have to be +1. So this should be positive here, that's positive here, so that's a minus there. Okay. That's enough mistakes for today. So using my logarithm rules, I get to this. And then I do exponent base e to both sides. The left-hand side, or the right-hand side here is just the exponential thing that we've done before. And I'm going to drop the absolute value and create a plus or minus here, but that plus or minus is just going to get absorbed up into the a. So now what I want to do is separate this so I can get the p by itself. Oops. Anyways, I was saying, but if I made another boo-boo here. So I need to backtrack a little bit. My apologies again. Oof. So if I look here, this is not going to separate for p's. What I would want is I'd want m minus p over p here, which I don't have. But if I backtrack just a skosh, I can get that to come out. So here, if I multiply both sides by -1, I get that. Now when I use my rules for logarithms, the positive part is the numerator, the negative part is the denominator. And then I can do my exponent base e to both sides. So that gives me absolute value m minus p over p equals a e to the negative kt. Again, e to the negative c is just going to be a constant. I can drop the absolute value and absorb the plus or minus just up into the a. And now if I think about m over p, or m minus p over p as m minus p over p minus p, I have that. So I can add the 1 over. Oops. Oh yeah, that's fine. And then divide both sides by m. And then we're going to have to, oops, flip And it does it. That separates my p. I'll call this p of t or whatever. That's great. The only thing left to do would be to figure out what a is. So we do that for p of 0. So if I do that, p of 0 is going to be m over a e to the, well, k times 0 is just 0 plus 1. So I'm trying to solve for a. So I would, let's make a reciprocal of both sides to get that a out of the denominator. Now at this point, just e to the 0 is 1. So 1 times a is just a. And then I'll multiply both sides by a, or m. And then we'll subtract 1 from both sides. And just make a common denominator. Which is what we wanted. Where a is then m minus p naught over p naught. And that is what we formalized down here. Took a minute to get there, but that's okay. So let's look at an example then. So if I look at this, I notice, hey, that is the form for the logistic equation. Oops, I got my stuff all out of order here. Put that over here. So I can just use this straight through, where here's my k and here's my m. Now, in place of a, I'm going to do m minus p naught over p naught. And then my k is that. So that's my function. So doing p of 40, all I'm doing is plugging 40 in for t. And I got the 9, just 1,000 minus 100 is 900. Divided by 100 is just 9. So to do that, just calculator time. So this screams, please use your fraction command, as the parentheses would be a hassle. And then don't forget your negative sign. So 731-ish. If I did the same thing for p of 80, so I'll just take that same thing and just put 80 there instead. It's 985. And then it says at what time, so we're solving for t here, does the population reach 900? Well, I already know it's somewhere between 40 and 80, right? But to solve this algebraically, I have this. So first thing I'm going to do is get the t out of the denominator. So I'll make a reciprocal to both sides. And then multiply both sides by 1,000. So that's going to reduce 1,000 over 900, just becomes 10 over 9. And we'll subtract 1 from both sides. So 10 over 9 minus 1 is just 1/9. I'll divide both sides by 9. We'll do the natural log of both sides to cancel out the e. And then divide both sides by negative 0.08. And that should be my t. So at that point, it's calculator time. Again, I'm going to use, the fraction command. This one, I guess it doesn't really matter. So I get 54.9. Ish. And that's all she wrote. At this point, you guys should work on the homework. That's going to be 1 through 11 odd, 15, and 19. Best of luck, and we'll see you next time. Oh, also, FYI, I did put the Chapter 9 test review and test review key into the OneNote, so you should be able to see that. All right, have a great day.